So today I'm going to talk about how the new age of optics, like the modern optics we say, is helping astronomical instrumentation, particularly the optical telescopes. And by the end of this lecture, I hope that you guys will share the same enthusiasm and excitement I have about how optics is driving the modern astronomy. So in this lecture, we'll basically go through we'll briefly go through the history of the optical telescopes, and then we'll see what we have right now and then what's there for the future. Then we'll see some of the challenges faced by these optical telescopes and how we are using or how we are countering and approaching those challenges. And then we'll see that there's still a bit of gap we need to bridge and what can be used from the modern optics toolbox, specifically photonics and sub-wavelength optics, to make this gap a bit smaller and work towards our goal. Following that, we'll see some on-sky examples we have right now, as in, like, when I say on-sky, the instruments that are being used as of right now that sits behind these telescopes. And finally, I would conclude with a bit of my work, what I've been doing since past 2 years. So a bit of history on telescope, really exciting, since the first lens-based seeing instrument which can magnify things was done by a Dutch spectacle maker in Netherlands in 1608. And 1 year later, Galileo Galilei was the first person who used this lens-based seeing instrument as a telescope and did the first astronomical observation. Then a few years later, Isaac Newton devised the first mirror-based telescope, which you can see it over here. It was a really small telescope, you can hold it in your hand, and it used two mirrors, one mirror which focuses the light onto a really small mirror, and then you can use an eyepiece as a detector to see the stars. Now, moving a few decades or even a couple of centuries ahead, we have VLT, which is a really nice 8.2 meter diameter telescope. For reference, this room would be around 23 meters, so half the size of the room, the primary mirror. And then the next one is Seward telescope, the same size, 8.2 meters. The VLT is in Chile, and the Seward telescope sits in Hawaii on top of Mount Mauna Kea. And we have another 10-meter telescope on top of Mount Mauna Kea, a twin telescope named Keck Observatories. So what do we have for the future? We have bigger telescopes. So now we want to make extremely large telescopes, size around 40 meters in diameter. So probably you can see double the size of this room, quite big. And then the ELT is planned to be in Chile again. Then we have 30-meter telescope, really nicely named. You can guess the mirror size is 30 meters. And then we have Giant Magellan telescope, again on top of Mount Mauna Kea in Hawaii, and that is 25.4 meters in diameter. So you can see that in just a couple of centuries, you went from something which you can hold it in your hands to something really, really big. And to really utilize and really push these telescopes to their full potential, you need to make your instruments very complex as well. Like the first observations made by Newton was basically through his eyes, and he drew stuff what he saw from those telescopes. And now you have these really fancy instruments which you need to use to really push the potential of these telescopes. So again, bigger telescopes means there are more complex challenges, and hence we need better and complex instruments which are better than our eyes. So what are some of the challenges faced by these optical telescopes? One of them is atmospheric turbulence effects. So basically, when you look through the sky, atmosphere does some really bad things to our seeing, and it really affects what we see through the telescope. That other thing is interferometry at optical and infrared wavelengths, which again I'll go through these challenges really slowly. And then our goal is to find Earth-like exoplanets, right? So we need to get good enough to detect these Earth-type exoplanets. So that is more sort of a goal and not a challenge, but it's sort of something we want to work towards. So again, there's a really big asterisk over there because these are not the only challenges, there are so many more. But these are some of the few challenges I would want to discuss in this lecture. Okay, cool. So atmospheric turbulence. You have a star far away from your Earth. It gives out flat wavefronts, which you can see are basically flat and nice. And when they pass through the atmosphere, basically atmosphere changes really quickly. You have wind speed, you have temperature changes, and that evolves quickly. And what that does is that the refractive index of your air changes at that speed. So because it's changing quickly, you cannot just fix it statically. You need to adapt to it. So to think this issue, you can think of it this way, that someone is putting a spectacle on you and the power keeps on changing. So you cannot really adapt to it by just putting an opposite power lens to your spectacle and just get done with it. You have to like quickly change it, and you have to change it as fast as the atmosphere or the wind changes, basically. And this is not something new. This was known back in the days as well. And Newton in his book said that the only remedy is a most serene and quiet air, and such as maybe perhaps to be found on tops of the highest mountains above the grosser clouds. And hence, if you remember from the previous slides, all the big observatories are on top of like mountains, and where the air is really quiet and basically are on top of the atmosphere. So why stop at the mountains, right? Like if you can go to space. So this image on the left is of Uranus taken by the Hubble Space Telescope, and on your right is basically something taken from a ground-based observatory, but there is no correction for the atmosphere. So you can see how the atmosphere basically blurs your image out, and you cannot see the details in the image. Right, so as I said, we need to correct for these atmospheric effects, and because we want to make bigger telescopes, we cannot just make big telescopes and send them to space. It's not feasible. So that's why we need to somehow correct these effects. And you can see if we correct for these effects and use bigger telescopes, we can do a better job at correcting it. So on the left, now we have the same telescope, but with adaptive optics. You are correcting for the atmosphere, and on the right you have the Hubble Space Telescope. So it's more sharper, and this is done with a combination of bigger telescope than Hubble and correcting for the atmosphere. So just to motivate a bit more, this is the image of the galactic center without the adaptive optics. So can anyone take a guess how many stars or like how many objects can you see in this image, like a rough estimate, maybe 10, 20, 7 or something? But if we turn on the adaptive optic system, it's a different picture. Like you have many more details, you have so many more stars, and especially in the galactic center, you can see that basically you can see maybe 1, 2, 3 objects over here, but there are so many more. So if you really want to use bigger telescopes, you need to use AO, and you cannot really send bigger telescopes to the space. So I have a really cool animation for you guys to like understand how adaptive optics works. If I can play. Yeah. So because of the atmosphere, your object basically moves continuously, and you use something called adaptive optics or AO. And what you do is shine a light or a laser to the sodium layer in the atmosphere, and that basically makes an artificial star in the sky for you. And now we know the position of that artificial star. And when you look at the artificial stars through the telescope, you will see that it moves. It's basically distorted by the atmosphere. But you know beforehand where you expect to see that artificial star you just created. So you can basically sense and use a deformable mirror to put an opposite shape using these magnet-type mirrors, and when the light from an actual natural star comes in, you can correct for it, and you can see that basically the wavefront gets flat. And when you apply those corrections, you can correct for those distortion explosion, and now you have your natural star where you want it to be. So this is a schematic of your generic AO system. Again, you have light coming from a star. It's distorted, so it's like squiggly, and you, with using the information from your artificial star, you can use an adaptive mirror or a deformable mirror and then correct it and make it straight. But to do this, you need to split the light such that one part of the light goes to a wavelength sensor, so you can sense what corrections you have to make. And the other part goes to your camera or your science instrument where you actually want to use the information you get from the stars. So what's going on over here is that because you split the light, you cannot really sense the errors. You have like really small errors due to lens or your air changes, or that there can be really small changes. And if we want to work towards the goal of finding exoplanets, then these small changes are they matter. So we need to find a way to somehow not split the path and sense these errors which arises because they don't share the common paths, and they are usually called non-common path aberrations. So since they don't share a common path, you have aberrations. So that is one of the challenges we have right now. Okay, moving on to the other challenge. So I'm pretty sure many of us remember this black hole image we made as a humanity a few years ago, and it was basically done using a really big Earth-sized telescope. So what we did was basically use each telescope, like the data from each telescope across the world, and you can basically save the data, as in you can save the amplitude and the phase you get from that object and save it on disk. Although be it really big, like in terabyte size, you can save it on hard disk and ship it, and you can process the data from all the different telescopes and make an image like this. So essentially you need to image something like a black hole at the galactic center, you need an Earth-sized telescope. But you cannot really do this at shorter wavelengths. So optical and infrared wavelengths are 10,000 times smaller than radio. So you cannot really, it's fast, and the phase and amplitude cannot be saved at these wavelengths, and this is because of fundamental limitation due to quantum nature of light. So just to give you guys a reference, radio waves are longer, and as you move to higher energy waves, the wavelength gets shorter, and we are interested in this region of the electromagnetic spectrum. Right. So that's the second issue, that we want to do interferometry, as in use telescopes, multiple telescopes to make an effectively bigger telescope. Right. So what's the third issue we have? We want to be good enough to detect Earth-like exoplanets. And basically the stars which have the exoplanet system are 10 to the power 6 to 10 to the power 9 times brighter than the planet. So as of right now, using the system we have, or the current technologies we have, we can only detect planets which are either far away or very big. So if you want to find for planets which are closer to the star, and there is one, so if you want to find Earth-like exoplanets, we need to basically suppress the starlight. So you can see that the starlight was overwhelming the smaller planet which was closer to the star, and we need to suppress it. And usually these Earth-type exoplanets are in what we call habitable zone, or the Goldilocks zone, which is not too far but not too close as well. And since they are like really bright, again 10 to the power 9 times brighter than the planet, we need to somehow suppress the light. So just as a recap, we want to make an adaptive optic system to correct for the atmosphere such that the sensing and the detecting happens on the same path. We want to make an interferometer at smaller optical and infrared wavelengths. And the third one is to get good enough to detect Earth-type exoplanets. Again, it's not a challenge, it's a goal. And in general, we want our instruments to be efficient, because you don't get enough light from these small exoplanets. They're really small, and whatever light you get, you have to work with it, and you don't want to lose that light in your instrument. Hence, you want your instruments to be as efficient as possible. So what do we have for that? So this is something I call like modern optics toolbox, as in some relatively newer optics. And specifically in this lecture, I would talk about subwavelength optics and photonics. And just to like show you that it's not something new. It was something known to scientists before, but they weren't just sure about what's going on. So this is like a picture from Newton's optics book, which he wrote in 1609, and he saw these really intricate images, and these are, by the way, hand-drawn, which is really fascinating to me. Like, to draw something like this, it's amazing. So these patterns basically happen due to the subwavelength nature of your electromagnetic waves. So we see this in nature all the time. As everyone knows, blue pigment is not really natural. If we see something naturally blue, there's probably something else going on. And a really good example for that is morpho butterflies. They are naturally yellowish in pigment, so if you look them from the back, they are sort of yellow, but if you look at their wings, they're blue. So what's going on over there? So again, what's happening is the white sunlight hits the butterfly's wing, and we only see the blue wavelength of light. So our eyes can see from red to violet, which is probably around 700 nanometers to like 400 nanometers. And what's happening is that the other parts of the white light is suppressed, and you're only seeing the blue one. So why is that happening? If we really zoom into these butterflies are a few centimeters in size, and if we zoom into their wings, we have these really small scales. And again, if we zoom in to those scales, we would see these really small structures. And these structures are basically 1/1,000,000th of a meter. And even in these structures are small details, which are like 60 nanometers, which is like 6 and 1/1,000,000th of a meter. So it's really small compared to the wavelength at which we are seeing here. So again, human eyes can see between 0.4 to 0.7 microns, and the smallest features on these butterflies are 0.06 microns. And just to like give you guys a drawing of the scale, it's something like this, where you have like ridges, and again, this really small portion is like 60 nanometers. So if you have a periodic structure which goes on, and if the size of those structures are smaller than the wavelength, so if the structures are smaller than the wavelength, then you would see something funny going on, that if this is material A and material B, then there will be some combination of A and B, and that is basically decided by what width A is, what width B is, and the type of material, like what refractive index you have for the material. So by tweaking A, B, and the type of material, you can like an effective material which you would like to make. And that's what's going on with these butterflies as well. That if the size is not smaller than the wavelength, if there's equal to the wavelength or bigger than the wavelength, then usually these periodic structures would just split the light. You shine a white light and it would split in different colors. But when you have these structures smaller than the wavelength, it would suppress the other colors. At least in the case of butterflies, it suppresses the other colors, and you see only this really nice blue iridescent color. So again, since the structures are really smaller than the wavelength, due to sub-wavelength phenomenon of electromagnetic light, or at least the visible light, you see suppression of other colors or other wavelengths, and you only see the blue light. So the takeaway is that if you use structures smaller than the wavelength, we can effectively modulate the material's response as required. So you can tweak these parameters, A, B, type of materials, N2, N1, and make an effective material which you can use for your own instrument, where you can basically modulate the response as you want. come to the next part, the photonics in our toolbox. The photonics is sort of defined as generation, detection, and manipulation of light. So we would sort of focus more on the manipulation part of the light. So to manipulate anything, you need to take control of it, right? Like you cannot just have it in like air. You want to have control on it, and we usually do that using chips. So what we are doing is try to have the light in the chip, and then you can manipulate it as you wish. Okay, so to understand what photonics is, or like first to understand how you get the light into the chip, let's look at this really cool demonstration about total internal reflection. So usually if you shine, this is a glass slab, this is air around it, and if you shine the light, it would usually refract at different angles, and as you change the angles, the angle of refraction changes, and at one point it will graze through the surface, and if you go beyond that angle, it will internally refract. So light is in the slab now, and it doesn't matter how far you go from that critical angle, it will stay in the slab. So what you can do is, you can feed a light through one end of a glass tube, and if you make sure that this angle is beyond the critical angle, it will stay in the slab. So that is the same thing as if you have air around it and you shine the light into the glass and it stays in the slab of your glass. Right. And this is one other example that it can be any geometry. It can be a fiber, like a big cylinder tube kind of thing. It doesn't have to be flat. You just have to make sure that the material is correct and the angle at which you put in the light is right. And then you can basically guide the wave through whatever kind of geometries you want. And a really extreme example of this is fiber optics cable, which is why we have internet. Basically, we send information from one continent to other and across the world using these fiber optics cable, where you have light in this really thin optic fiber cables, and it's basically surrounded by some material to make sure that it's internally reflected correctly without much loss. So the only thing really important to us is to make sure that the core, which is the material itself and the surrounding, has the correct refractive index, or they're correctly aligned to make sure that we have the total internal reflection. And there are many flavors of this. You can have something like this where because the silica and non-silica has a really different refractive index, it makes sure that the light stays in this really small slab. And the same with something like this, where you have you have a material surrounding another one from three sides, and you can guide the wave through that as well. And you can make different geometries out of it. You can have a straight waveguide, you can have something like an S-band where the entrance and the exit is like far apart and not in the same line of sight. You can split the light, you can combine the light. Then you can have something like where you first split the light and then again combine based on how, like you can do something over here where you can maybe put some kind of modulation over here or something. Again, with something like this, where you do something where one light goes from here and then it jumps to the other waveguide. So you have a lot of different options to manipulate the light. But the important thing is that for us to understand that there is a way to first confine the light into something like a flat chip and then route it the way you would like. And this is a very generic schematic of a photonic chip where you have like a way to put in the light into the plane of your chip and then route it the way you want. And you can, the modulator I was talking about, you can change the phase and as you wish, basically. And to give you guys a sense of what the size of these chips are, they are usually really small. So 10 millimeters in size, and for reference, a euro coin is 23 millimeters. So probably the size of your nail. So really small. And why this works in our favor? Because if your light is confined in a really small space, you can control it, as in it is not affected by the environment that much. You can do the same things you're doing on a chip, but on a table, but that is so much more different, because let's say if we are walking across the table, those vibrations would affect the way the light is interacting. So having something really confined on a really small space, having the light confined in a really small space is advantageous for us. And this is really a boon, I would say, because of the silicon industry, because the manufacturing of these chips are basically made possible by the silicon industry, which is used for making these semiconductors for phones, laptops, and so on. So again, the takeaway from the photonics part is that now we have a light where we can confine the light in a small space and manipulate it based on how we want. So moving on to some on-sky examples, which is the VLTI at Chile. So we have this optical interferometer where we are using these 4 telescopes, each of size 8.2 meters, and we can combine the light from each of these 4 telescopes and make the effective size of your telescope up to 200 meters. So you're basically having a big telescope, as we like similarly we did for the radio interferometer, where we made the telescope the size of the Earth basically. So how are we doing this? We have time, so we can go through the whole animation, but I have this video where it basically traces how the light comes from the star and how it's combined using this gravity instrument. So you have light coming in from the star. Oh, sorry. Sorry about that. So you have your light coming in from the star, and then it's observed at each of the 4 telescopes over there. Bounces off the mirrors so that we can use the light in the basement of these telescopes where the instruments sit. This is the adaptive optics bench of the unit telescopes, where you split the light, and now one of the light is going into the wavefront sensor, which we'll see. Yeah, so this is the wavefront sensor. It basically sees how much each of the speckle is moving, and it gets information from that about how much correction you have to apply to your science light. So we'll go back to the part where we split the light, and now this is the science light, and the science light from each of the 4 telescopes are sent through tunnels. They have like these really big tunnels. And you send the light from each of the 4 telescopes into another instrument facility in the basement. This is the gravity instrument. And again, you use so many mirrors to just route the beam and make sure the beam goes where you want it to go. So you split the light again, and the gravity instrument has its own adaptive optics system to make sure that the small changes you have from your unit telescope to the instrument is corrected as well. And now we feed this light into fiber optics cable I just talked about, and they are usually easier to route through your instruments, and you can use small spaces as well. These coils are just to make sure that the light from each telescope travels equal length. You don't want one light to travel more length than the light from the other telescope. So these coils make sure that they travel the same length. And there's some more routing of your light before it goes into the photonic chip. And this photonic chip, what it essentially does is it combines the light from all the 4 telescopes and then splits into multiple parts. So you can feed that multiple parts into a spectrometer. And what a spectrometer does, it basically distributes, splits the light, and that helps to characterize whatever object you are looking for and find out what molecules you have from that object. So again, what this whole video does is it shows us an example of how adaptive optics works. You need another adaptive optics for your unit telescope and before you combine as well. We are using fiber optics cable for moving light into really these small intricate spaces, and it also uses photonic integrated circuits for beam combination from each of the unit telescope. So just to talk a bit more about the photonic chip which we are using, it's 50 millimeter in size. You have light going in from each of the 4 telescopes. You first combine them based on a phase and then split them again into multiple ports. You can feed the light from multiple ports into a spectrograph. So you can do this using bulk optics, but it would take probably like a big bench like this, and it won't be efficient because again, there are some vibrations going on and stuff like that, which would make this combination and splitting of light again really inefficient. So using something like a 50 millimeter chip, which you can probably hold it in your one finger, which does this thing, is really impressive to me at least. Now, the other instrument I would like to talk about is L.A.D. It sits at the Subaru telescope in Mauna Kea, Hawaii. So what is nulling interferometer? Basically, if you have your light, so this black circle is your telescope, and if the light from the star hits the center, and if the light from, let's say, an exoplanet is off axis and not at the center, you can feed the light from each part of your telescope into, this is a photonic chip again as well, which is probably 7 millimeter in width and 40 millimeters in length. And you can do efficiently, you can route the light in such a way that first it splits the light from star, your planet and the star. So it splits the light, and then you combine the starlight and the planet light in such a way that there is no light in blue, yellow and purple waveguides. So essentially you null the light from your star, and all the light you're getting from is from this red waveguide, which is the light from a planet. So interfere the light in such a way that the starlight is essentially reduced or nulled out. So this is the integrated circuit which they use to do this. It's made of glass, you cannot really see anything, but essentially this is the top view of the chip. And all the splitting and the coupling happens at the probably last 10 millimeters of the chip. So this instrument was quite significant in the sense that it was able to bridge the gap, as I said, and was able to reduce the starlight by a factor of 10 to the power -4. So to remind you guys, our goal is to go to -9 so that we can detect these Earth-type exoplanets. So moving on to the things I have been doing. So this is I worked on simulating photonic chip which sits at the focal point of your telescope. So you have your light coming in from the star, it gets emitted by the atmosphere, you have aberrated wavefronts, it goes through the telescope, and if you feed this light from the telescope into the chip, it basically corrects for the atmosphere, and you can efficiently use the light without splitting. So essentially this way of correcting for the atmosphere, or this way of doing adaptive optics, you don't need to split the light, and it uses integrated circuits. Again, it's not a perfect way of doing it. You do lose a bit of light, but again, the goal is to inch towards our challenges and trying to solve them. So what I specifically worked on was simulating each part of this photonic chip. So you have something called a grating coupler, where you shine the light in and you can couple the light into the chip. Then you have something like a beam combiner again, where the light from each part of your telescope aperture is combined, and you can use these kind of phase shifters. This is the part where you can change the phase of the light in such a way that you can correct for the Earth's atmosphere. It also uses like sub-wavelength based waveguides to like increase the size of the light so that you can couple it into optical fibers. So what I did was basically do an end-to-end simulations of each of these components of your photonic chip and estimate the performance. So basically that tells us how efficiently we are doing this adaptive optics system. So when I left after doing the simulations at U of T, they based on the work I did, they manufactured this photonic chip. Again, this would be something like 40 millimeters in size, and these wires you see are basically connected to the phase shifters, where you can like give current and change the phase of your light. And again, this is the test bed which they use to test out these chips. As you can see, like this is like a really intricate system where you have so many optical elements, and this is sort of things which we want to avoid. Like we don't want something like this to sit behind our telescope, where even like moving or some small seismic activities ruin what you're measuring, right? So that's why having a photonic chip is really useful, since the small vibrations and stuff like that doesn't affect what you're measuring. And now, right now, since past 1 year, I'm using these small sub-wavelength structures to design efficient instruments. Essentially, this is a diffraction grating where you have light coming in and it splits the light efficiently. And the way we use these small sub-wavelength structures is to like manipulate for our need, as in at what angle we want the light to go and at what wavelength we want the light to split. And this is really useful for faint exoplanets, because anyways we have really less amount of light from these exoplanets. So having an efficient instrument where you don't lose whatever small light you have is useful. So this is some of the things I wanted to talk about how photonics and sub-wavelength optics are basically used to make complex instruments such that you can make better, you can push the limits of your telescopes, especially since the telescopes are getting bigger and bigger. And I would like to leave everyone with this really nice image of the L.A.D as of January 2025. And as you can see, they have this 39.2 meter mirror I was talking about, and they have the structure ready for it. And just to give you guys about how old optics is, this is a hand drawing from Newton's book, and it's just fascinating how things which we use computer for now to do stuff, they just hand drew things like that. So thank you so much for your time. I hope you.
I'd like to thank Dhwanil for such an interesting lecture, and I encourage you all to ask questions if there's someone like that.
What you described us in terms of for amplifying light, etc. What does that mean to the signal? What the noise ratio in terms of airglow and so forth?
So when I say amplification, you cannot really amplify your signal. So I think you're referring to this definition of photonics, right? Right there. So again, you cannot really amplify your signal using photonic chips, right? Like you cannot make up your signal. So the signal to noise ratio, which you're probably talking about, is how efficient your chip is. Is that what you mean? So if you have an efficient coupling of the light from, let's say, telescope into your chip, that would affect probably the signal to noise ratio. Yes.
Would all wavelengths go into the photonic chip at the same time, or is it split before?
No. So that's again a very good question. So let's see if I have anything for that. No. So the way this light gets confined into the glass is dependent on the wavelength and hence the material around it. So there would be a small, these are narrowband instruments. So let's say if you optimize your chips for 50 nanometers, then it would be fine enough for probably like 1500 to 1600. So, but not more than that. So probably full width half-max of like 100 nanometers, something like that.
And what is the wavelength range which you observe in this way?
What instrument are you specifically talking about?
No, yeah, what you told here, the things.
So it really depends. For example, the VLTI gravity chip, where is it? Yeah, this one is made for, I would say, 2 microns. So
Okay, so that is the
near infrared.
the near you use it for the near infrared is the answer.
Yes.
I expected something because in the visible it is very difficult, huh?
Exactly. So for visible, you would have to use some different materials. So silicon on silica is really good for near infrared, so probably 1,000 nanometers to 2,000 nanometers.
Yeah, that is still that is still infrared 1,000 nanometers.
Yeah,
that is
that
my
is
micrometer, and the red is till 800 nanometers or something like that. And then you cannot see, but what is really interesting would be, can you also go to the blue light, to the 400 nanometers, or is that impossible with this method?
No, so it is possible. The only reason we started with infrared was because we had this skeleton from silicon industry, right? They use silicon and silica for semiconductor chips. So we realized that works really well for near infrared and infrared, and you can do for optical as well. Like right now, we have titanium oxide on something like lithium niobate oxide or something like that. You can basically change the material such that it's optimized for whatever wavelengths you want. So it is possible, people are doing it, but just because we have this silicon industry, we can just because the process is the same. It's essentially the same process which you use to manufacture these semiconductor chips. So we can just use those facilities to make our photonic chips. And that's why people started with near infrared, but right now there are works where you can go probably to like 500 nanometers to 600 nanometers. But the only thing is that you have to change the material, so the silicon on silica would not work.
And how is it with, because the short wavelengths has much more problem with the seeing, so they are coming in much worse in wavefront than the longer wavelengths. And
exactly.
And can you solve that for the shorter wavelengths? Or
solve that? Maybe. Like we can always, like the goal is to always go towards something, right? Like solving in one go may not be possible, but like maybe we work towards individual goals, and something happens, and now voila, you have probably a working chip for like UV light. So
But a wavefront correction that is good for the shortwave infrared would not be good for the UV, would it?
So that is again a very good question. It would be if you make sure that So it would be if you make sure that you sense in the shorter wavelengths and correct for the longer ones. So that's what we do. When we split the light, at least right now, we sense the corrections in shorter wavelength to overcompensate sort of the corrections for the longer ones. But the chips which we talked about again are really narrow band, as your question was asked. So in that case, it really doesn't matter about how you're sensing and how you're correcting.
Yeah.
Okay.
Some questions.
1, 2, and then. So,
Could you give us an idea about the price of such a...
that's an amazing question. So I cannot say for the price for other chips, but the chips which my group at U of T made, so this guy, I think this was, it was definitely not more than 100,000 Canadian dollars.
What? What do you say?
So less than 100,000. Yeah. So I would say probably something like 50,000 to 60,000 would be like a median sort of thing.
For one chip?
Yeah, it really depends on how big of a chip you have. So if it's smaller, then it would be cheaper, and if it's bigger, then again it would just. And it also depends on what material you use. It also depends on what you want to do. So like having these wires bonded to your chip increases the complexity.
And what is the reason of the price? When I say I do not want one only, but I want 100, it is much lower the price?
Then the price changes. Yeah.
So the development are the large costs.
Yeah, these facilities are basically research facilities, so they are not built for scalability, right? So that's where the price changes comes in. I think. Maybe
a little bit of a different question. I assume if I've understood it correctly, you're trying to counter for the dynamic distortion of the light coming into the object you're looking at.
Yes.
This is all done physically, which is very impressive.
Yeah.
I have no idea, but are you using some sort of software or maybe even artificial intelligence to help counter for that distortion? Would that be a way to go? To improve it even more?
Yes.
To get to your goal of finding the planet that might have life, which for $100,000, by the way, is not a lot of money.
That's an excellent question as well. So using some sort of machine learning for this part of your optic system is definitely something people are doing, but we don't want to train a machine learning algorithm to find exoplanets, because if you train it to do that, it will find you one no matter what. So, but yeah, it's you want. So again, since this changing of atmosphere is happening really fast, it's probably 10 kilohertz or something, very fast. So you have to like make sure that your control system is like fast enough to catch that. So you want your algorithms to be optimized. So that's where you use machine learning, rather than like just asking it to use some data and find your exoplanet. But that is again something which people are doing, where you can use machine learning for better optimization.
The more accurate you're doing this, the better that will be able to work.
Yeah.
It all starts with measuring correctly.
Oh yeah, for sure. So the measuring part is so much more important. Like we have so many different types of wavelength sensors as well, and yeah, different types of natural the artificial stars I mentioned as well, to make sure that we use them efficiently and in a better way.
So you mentioned some adaptive optic systems, and we know that recently there's some new adaptive optic systems with new wavefront sensors that are using interferometry to reconstruct wavefronts. You also mentioned that there are chips that can interfere light. So my question is it possible to move away from geometrical optics to induce phase shifts to then do to chips. And I guess a good preceding question to that would be, what happens to the wavefront information once you feed light into, let's say, fiber optic?
Right. So, okay, there are a few questions in there. So, your first question was basically if we can use chip as a wavefront sensor, if I can like condense your question into one part. So, yes, you can do that, or you don't even have to make it a chip. You can like make a big, so it's called a photonic lantern, where you have essentially a big fiber cable with small, like small cables into it. So, it's not an on-sky instrument yet, but people are using those kind of photonic lanterns, which goes in place of a wavefront sensor, just to like see, as you said, like use interferometry as wavefront sensing. So that is one part of the question. What was the other one?
Well, I was wondering, well, I know interferometry is already being used.
Yeah.
But it uses geometrical systems like mirrors or lenses to induce some kind of phase difference. But I was just wondering, has work been done, or is it even possible to do this kind of adaptive optics, but on smaller scales like chips? Right? Because you mentioned that you want to try and minimize the scale to reduce effects of, let's say, vibrations.
Yeah. So the phase part which you're talking about, you can change the phase of your light. So essentially, this is a phase shifter where you have a metal heater which goes through these light through waveguides. And when you heat these waveguides, the refractive index changes, and that's how we can change the phase of your light. Because since changing the refractive index means your light has to travel more through a sort of a different material, so it adds an extra bit of path for your light. So that's how you change the phase. So yes, it is something people are doing. And again, the goal of using photonic integrated circuits is to reduce bulk optics in your instruments, because detecting an exoplanet means that your system cannot move for like cannot move more than like nanometers. If there are vibrations on the scale of nanometers, then your signal is basically distorted and it's gone.
And do fiber optic cables lose any of the wavefront information, like the aberrations of the wavefront?
Yes. So let's say you have a fiber optic cable that runs for 1 meter, then you would lose a sort of a bit of light, maybe like 0.01%. But it really doesn't matter in astronomy, because the plan is not to send the light from your telescope thousands of kilometers. You'll probably go to some basement underneath the telescope. So in that case, it's not an issue. But you do lose a light when it goes through waveguides.
I don't mean so much as intensity, but in terms of the actual aberrations that you have.
Oh, yeah, no. So those stay the same. Like the wavefront which you have once, like the waveguide, when the light is confined in your waveguide, it doesn't change. Like what you see in the two ends is the same. Probably the only effect would be, as I said, the attenuation. We call that the decreasing of intensity.
Is there light energy lost when you couple the light coming from let's say, the telescope into your chip?
Yeah. So these are the grating couplers. So you have your light coming in from the telescope, and it slowly couples your light into this chip, and this is the part where you lose the light. So if I would say the best grating couplers are like 95% in terms of efficiency. But there are also multiple ways to couple the light. Like you don't necessarily need a grating coupler if you sort of make sure that your focused light is really going into. So let's say this as an example. So let's say you're sending light from a fiber cable into the chip. If you make sure that it's aligned correctly, then you don't really need to use these grating couplers. But yeah, there are multiple ways of coupling your light into the chip, and those are not completely 100% efficient. If that was your question.
You said right now we can decrease the star light from the planet light of 10 to the -4. How do you think we can get it even lower? So we can reach 10 to the -9.
Yeah. Yeah, so it could be a whole new talk on that. So we have something called chronography where you essentially mask this light in such a way that it's masked completely, and it interferes in such a way that the light from the Earth or the exoplanet is not known. But again, it's something we are working towards, I think, I guess. But I think the best chronograph right now can null up to like 10 to the power -7. So it is quite cool as well, but those are not, like those are still in lab instruments. And that's why like I thought might not show over here.
I think we have time for one more question. Otherwise, I think Dhwanil will...
A very silly question. How much time would you need in order to detect a planet going around a star? I assume that varies a lot.
Yeah, it depends on the orbit of your star, right? Like of your planet. So if it has a bigger orbit, then it would take more longer. But the thing is that we don't know if there is a planet, right?
No, you don't know from the...
Yeah, exactly. I had a really nice quote by someone. It's not that, but no. But it was basically like, if each one of us even spent like 60 seconds to find an exoplanet for like just 1% of the stars we know, then it would still take us 60 years. So it is something, really difficult, I would say.
Question. You said, I think, that it is difficult or impossible to have a large telescope in the space. Isn't it possible to have it in small pieces and assemble something on the moon, for example?
Yeah.
Other plans for that?
Yeah, so it is possible, but again, it would be for radio wavelengths, since there would be no way to have your data feed from moon to Earth, right? So you can have a radio dish on moon, you can have radio dishes on Earth, and then essentially make a radio telescope as big as the distance from Earth to moon. So it is possible, but not for shorter wavelengths.
Very interesting questions. Thank you so much again for the talk.
I hope you